So let us start. Well, as food scientists, food engineers, when we were not, especially the newcomers to our lab, are not very familiar to basics of NMR, and that is why I usually recommend them to read one long and one short reviews which have been published from our group. So these are dealing with the food applications. So if you want to increase your knowledge and awareness on how time domain NMR can be used for food applications, so these two reviews can be good resources. Okay, so let's first start with the basics. And nuclear magnetic resonance belongs to the family of spectroscopic methods. And we know that when you talk about the spectroscopic method, we usually refer to a different region in the electromagnetic spectrum. And in terms of nuclear magnetic resonance, we usually talk about the radio frequency range. And if you look at the frequency range where NMR can be used, you see we talk about, you see the radio frequency range in the table. And we have, and the shorter the wavelength, normally the higher the energy. So compared to X-rays, gamma rays, we're talking about lower energy levels in NMR analysis. So if you look at what are the spectroscopic methods based on, and we know that in SuChAQuality, NMR is not the only spectroscopic technique that we will be using. And tomorrow we have a full day mostly dedicated for IR and data analysis. So usually the bond energies or the stretching, vibrations give us information by using the NIR spectroscopy. And whenever excitation takes place on the electrons, for instance, the electron spin transition or the atomic and molecular electronic energy levels, the fluorescent spectroscopy could be the way. And for the atomic nucleus, usually we talk about the proton, carbon, phosphor. So these are different types of nucleus that can be excited. And this type of environment is the one, this type of atomic nucleus is the one that we have our focus in the case of nuclear magnetic resonance. Well, NMR is able to give much more structural information than UV visible. For instance, if you look at cholesterol molecule, with stretching and bending, we can obtain a spectrum, or in the case of, and usually these stretching and bending will belong to, let's say, the OH groups, methyl groups, so we obtain a fingerprint pattern. In the case of UV visible, we can obtain information about the olefin ring. But if you do, let's say, NMR spectroscopy, and if it is high resolution, you will obtain really a very good characterization of the molecule. Well, the history of NMR can be divided in several distinct periods. So theories on atomic nuclei, we see beginnings of 1920s, and then first NMR experiments, early structural analysis by in organic chemistry, first quantum leap in technology and methodology in 1966, and then in 76, the rise of biological NMR, so use of NMR in biochemistry, and then from 86, the second quantum leap in technology and methodology, and now we see even NMR systems that are working, that are like called zero field systems, or we have now very high resolution NMR systems, which gives quite nice high resolution profiles at lower detection limits. It's very low detection limits. Well, here you see some NMR instruments, which are usually what we call as high field systems. And these systems you see on the figure, like they are operating at a frequency of 300 megahertz, 400 megahertz, or 800 megahertz. And even there are now instruments that operate even at a higher frequency than the ones that you see here. So in an NMR system, in such an NMR system, as you see, it's a very bulky instrument. And usually we have a tiny tube having a sample volume of 3 to 5 millimeter sample volume. And then you put it into this instrument. And when the frequency is that high, usually these systems also have a quite nice homogeneous magnetic field, which is letting us to obtain a very nice NMR spectrum. And over there you see a molecule, for instance. And in this molecule, the different side groups will show different peaks on the spectrum. And based on these peaks, you can classify, you can categorize your molecules of interest. And this approach, where we use NMR for chemical characterization purposes, is usually the way we call as NMR spectroscopy. And fluidomics, metabolomics approach are usually the approach which are the fluidomics or metabolomic studies relies on the use of these high resolution NMR spectroscopy systems for chemical characterization. Professor Hussein yesterday mentioned about the use of NMR for characterizing, for instance, the sugars. In fact, the NMR that he probably mentioned is this type of NMR, where a chemical profiling will be provided. And I can show you some more examples. For instance, here you see the spectrum of ethyl acetate. You see different peaks at different chemical shifts. So all the presence of all these different peaks, as seen by the color of the hydrogen atoms, normally all belongs to the ethyl acetate. So in an NMR spectrum, a single molecule is not usually seen as a single peak. The hydrogen atoms that are attached to the carbon, so with different couplings, they show different peaks. So in that spectrum, all the peaks that you observe are coming from ethyl acetate. Or in the bottom, you see the spectrum of ethanol. And again, there's a color coding. So for instance, the hydrogen that is attached to the hydroxyl group has a different chemical shift, or hydrogen that is attached to the first methyl group has a different chemical shift, and the the hydrogens that are attached to the second carbon atom is appearing at a different chemical shift. And all these in together are representing the ethanol spectrum. So in NMR spectroscopy, we can obtain such a detailed classification or characterization. And as the molecules become larger, the spectrum will become more crowded. Over there, you see a protein NMR spectrum, for instance, and you see how crowded that spectrum is. On the right, you see the NMR, proton NMR spectrum of balsamic vinegar, and you see the presence of different components, acids, organic acids, and sugar. And such an approach can be used to understand, for instance, adulteration in the case of balsamic vinegar. Or this can easily be implemented to honey. It can easily be implemented to olive oil. And you can perform such spectroscopy measurements to obtain this to obtain information about the components that exist in your sample. In the bottom, you see 600 megahertz NMR spectra of maple syrup. Well, maple syrup is unique to Canada, and it is a unique syrup containing 60% sucrose, and also it has its original flavor and also has vanillin in it. And maple syrup, the spectrum is shown in the bottom. It is the pure Canadian maple syrup, and manufacturers, due to the cost, usually try to mimic the maple syrup by using corn syrup as the main agent, and then they add flavors and they produce pancake syrups. And in the top you see one of these table syrups NMR spectrum, and you can easily, just by looking at the spectrums qualitatively, you can say that these spectra are different from each other. The important thing is, whenever you have such spectra, data processing, of course, will be a challenge. And identification of the peak, so you have a large data set, and when it becomes a larger molecule, the data analysis will be even more difficult. For instance, for proteins, even two-dimensional NMR experiments are preferred to get more information. So data processing and interpretation requires some time, but that is what is usually done in foodomics or metabolomics studies. So for clinical nutrition applications, such high-resolution NMR spectra are analyzed to obtain information. But for that, again, a good statistical analysis and also data analysis skills are required. Softwares are also capable of doing the data analysis on the NMR spectrum. You have to have the insight on what the spectrum, or what are the components of the spectrum, to make the interpretation correct. Well, these type of NMR systems, the spectroscopy systems, as I told you, usually use a very short, very small tube, which has a sample volume of 3 to 5 millimeter. And this short volume, the small volume, is usually filled by a liquid. But when we talk about foods, always conducting high-resolution NMR experiment by using such a large instrument and costly instrument might not be the preferred way, because not only in terms of cost, but also in the data analysis and the data that you obtain. So for research purposes, the spectroscopy, NMR spectroscopy will provide valuable data, but for characterization of foods, mostly will rely on low and medium field systems, which means we are working at a lower frequency. So the one that I showed you were working at 300, 400, 600 megahertz, and now there are even lower field systems which are also capable of doing spectroscopy. For instance, there is the company Magritech, which is producing magnets operating at 42 or 60 megahertz, which is capable of doing spectroscopy. In other words, this chemical characterization. And in order to do that, as I told you, the sample volume usually should not be that high, because to obtain a nice spectrum for good chemical information, the sample volume should be small, and the homogeneous magnetic field in the NMR system will correspond to that small volume. And if your sample is big, then it might not fit to the homogeneous magnetic field in your system, and that could introduce bias to your data. So for food quality purposes, usually we are working with systems having magnetic field strength that is less than 1 Tesla. And here you see some example instruments, and I will also show you the ones we have in our lab. But these systems are usually operating, let's say, 20 to 30, maybe maximum 42 megahertz. That corresponds to 1 Tesla. And these are known as low field system. So LF NMR, low field NMR, is usually the term that you may see in the literature, in the publications. And low field NMR usually does not provide you chemical information as we observe in the other NMR spectroscopy systems. Because in these spectroscopy systems, once you acquire the signal, you usually apply a Fourier transform, which helps you to identify the peaks coming from the different protons. And in the case of a low field system, after Fourier transform is a mathematical transformation which converts the data from time domain to the frequency domain. And in the case of LFNMR, the Fourier transform, chemical shift dispersion, is extremely limited, and basically all protons contribute to a single resonance. That is why we cannot use it for spectroscopy purposes. In other words, if you put that ethanol, for instance, this sample that I have discussed in the previous slide, to one of these systems that you see here, you will just obtain a single peak. Why? Because my homogeneity and my field strength is not sufficient enough, and the chemical shift dispersion is limited. So we have just all the protons contributing to a single resonance, which will be seen as a single peak. However, we know that by using low field NMR, we can do many other stuff which can easily be related with food quality applications. And even, for instance, we know that LFNMR can be used to study the dynamic properties of the polymer chains. Okay, let me show you one NMR system, which we currently modified this system to a flow, continuous flow NMR system. Here you see the red box is where the spectrometer is, so the RF pulse is being generated from there. And on the right, the metal block is the magnet. We have two discs that are looking at each other, and in between these discs there is a radio frequency coil where you put the sample, and the sample is a 10 mm tube. So you see we have switched from 3 to 5 mm to 10 mm, which is giving us a lot of flexibility in terms of working with foods. And then you put your sample into that radio frequency coil, and then you start your spectrometer. It sends the RF pulse, your sample is excited, and then the RF pulse stops, and we obtain a signal, and then we analyze the signal. This system that you see here doesn't have any temperature control. That's why, depending on the laboratory's temperature, the magnetic field fluctuations are absorbed, and it is automatically reflected on the frequency. And this system, at its optimum temperature, is a system which is operating at 0.52 Tesla, which is corresponding to a proton frequency of 22.4 megahertz. So you see the frequency is quite low compared to this high resolution systems that we talk about. And here you see another NMR system. This is a system where it has been built by the resonance systems, and resonance systems in fact, this also has gradients in it, which means it is kind of capable of doing imaging, but we still don't have the very desired software. Dr. Grunin is always helping us to create a nice software for imaging part, and 0.32 Tesla, which is corresponding to 13.5 megahertz. And the sample size in that case is 16 millimeter, which lets us to put, let's say, an olive directly into the tube, or we can put a hazelnut to the tube, and we can do analysis on these individual food samples without doing any other extra preparation. So we don't need to put a solvent, so we can just put these particle foods and do our analysis. Or whenever, let's say, we work with confectionery products, we cut the confectionery, we can easily put to the tube, and then we do the analysis. But the main difference between these systems and the one that I talked initially are the high fields, and these ones are the low fields, which doesn't let us to obtain a chemical characterization, but which lets us to do some other analysis, which I will explain in the rest of the lecture. For instance, how the status of water is in your sample, or you can quantify oil content in your sample, maybe water content in your sample, how water status is changed, like free water versus bound water, water polymer interaction. So different applications are possible. In terms of a candy, we can also measure moisture content. We can obtain information about the water activity, because the water binding is going to be one of the information that we get in such a system. Okay, and let me show you another system. This system is a 20.34 megahertz system. It has a 10 millimeter RF coil, so the sample size is lower, but this system has comparably much better magnetic field homogeneity compared to the other systems that I have shown you. So that is why, for instance, the system can do solid fat content measurements in a very accurate way, or we can work in solid samples like powder samples easily with this nice homogeneous magnetic field, because whenever you have a homogeneous magnetic field, the higher the homogeneity of your system is, the better signal you will obtain, and better signal will give you better results in terms of interpretation. So this should be the first thing that you should think in your mind about the difference between high resolution NMR and the low field NMR. In low field NMR, we do not have a chemical quantification. Like, again, I'm giving example. You have an oil sample. Whenever you put your oil sample into this low field NMR tube, it will not tell you which fatty acids are present. But on the other hand, if you put into the high resolution system, it will tell you, it can tell you which fatty acids are present in that oil. But this one will not be able to give you that unique information, but it will give you some other information based on the measured parameters. So here are some basic terms that we are going to discuss when we talk about NMR. So spin, precession, relaxation, T1, T2, pre-induction decay, T2 star, RF pulse, signal to noise, time domain, Warmer frequency, Fourier transform, which I slightly mentioned, multi-exponential behavior, spin echo, self-diffusion, flip angle, gradients, and so on. So upon completion of these NMR lectures, and we will have more depth NMR NMR training school later on, so you will get familiar with these concepts. Okay, so let's talk about some basic theory. So NMR spectroscopy relies on the existence of the nuclear spin, which is denoted by I. This spin is an intrinsic property of the diverse atomic nuclei. In quantum mechanics and particle physics, spin is an intrinsic form of angular momentum carried by elementary particles and atomic nuclei. In some ways, it is like a vector quantity. It is a magnitude and it is a direction, but quantization makes these direction different from the direction of an ordinary vector. All elementary particles of a given kind have the same magnitude of spin angular momentum, which is indicated by assigning the particle a spin quantum number. Atomic nuclei contains nucleons, which are protons, neutrons, which both carry a spin. Depending on the number of the nucleons, there are different combinations of the nucleon spins to form a net nuclear spin. So, what does that mean? The basic principle behind the NMR technique is the nuclear magnetism. Nuclear magnetism emerges from the spins of the nucleons, which are protons and neutrons. In order to obtain a net nuclear magnetization, the nucleus should contain an odd number of nucleons. For the experiment, any element with an odd number of nucleons can be used, but in NMR experiments, the one that we usually use is the hydrogen atom, because we know that most samples, biological samples especially, and in that category we also talk about the foods, we have significant amount of water, so we can easily get signal out of it. Even from oil, we have protons, which hydrogen protons, which enable us to obtain signal. So any element with an odd number of nucleons can be used. So hydrogen is preferred. And this also hydrogen, as I said, hydrogen's abundance in organic sample, and also high MRI, high magnetic resonance sensitivity. So in that regard, we can talk about an NMR active nucleus term. So most elements possess at least one NMR active nucleus, but many in order for an atom to be NMR active, the spin quantum number must not be equal to 0. If the proton and neutron number are even, the spin quantum number will be 0. Both carbon-12 and oxygen-16 will not be observable, but carbon-13, hydrogen-1 and oxygen-17 are NMR active nuclei. Nuclei with a spin quantum number larger than I equal to 0.5 often show broad lines because of their quadruple moments. And there's a significant difference in the abundance in these NMR active nuclei, and the sensitivity of these experiments also differs quite a bit as well. So here, for instance, you see for carbon-12, we say that it is not NMR active, and for oxygen-16 it is not NMR active, but proton-1, so with just one protons, it is abundance is quite high, and it is NMR active. On the other hand, if you look at carbon-13, we have, okay, in this table, yeah, for the carbon-13, we say it is NMR active nucleus. However, the abundance is not that high, which means that, for instance, in a carbon NMR experiment, that will automatically be reflected as a lower signal to noise ratio, and the carbon NMR experiments might also take longer times. So we talked about the property of the spins, and in the absence of a magnetic field, the spins in a sample are randomly oriented. But when a magnetic field is applied, they line up parallel to the applied field, and in that case, either the spin is aligned or spin opposed. The more highly populated state is the lower energy spin state in the spin aligned situation. So you see here in the slide, the spins are processing with a certain frequency, and in the absence of a field, they are just randomly processing. On the other hand, if they have been exposed to a magnetic field, they start to align themselves in parallel or in opposite direction. So you see some of the spins are parallel to the magnetic field, some of them are opposite to the magnetic field. And then, so this alignment will be creating a net magnetization, which will later be giving us the NMR signal. So the spins, we say that normally are processing at a frequency, and especially when we expose them to a magnetic field, they are going to start to process at a frequency which is proportion to the magnetic fields that they are exposed. And over there, you see that the frequency is linearly proportional to the V0 magnetic field. So, and gamma sign that you see over there is known as the gyromagnetic ratio, and this is something that depends on the nucleus that we are studying. What does that mean? For instance, for hydrogen, we have a different gyromagnetic ratio. For carbon, we have a different gyromagnetic ratio. That is why when we are usually referring to the frequency of a system, we usually need to tell for which atom we are talking about this frequency. For instance, when I talk about the systems in our lab, I said that this system is operating at the proton frequency of 13.52 megahertz. So the protons do not directly face the external magnetic field all the time. So they make a spin top-like movement called precession, as you see in the figure. So this is not this precession is like a spin top-like movement. And as I told you, this spinning frequency is proportional to the magnetic field that the spins have been exposed. And this frequency that we are referring is usually known as the Larmor frequency. So this omega that you see is denoting as the Larmor frequency. So whenever I say you 300 megahertz system, 400 megahertz system, or 13 megahertz system, in fact, I'm referring that frequency. And all the protons in a sample have the same frequency owing to the relation above. And to acquire a signal from a sample, it is initially placed into a large static magnetic field. And for this purpose, a variety of magnets with a wide range of field strengths can be employed. When placed into the magnetic field, protons within the samples align themselves with this external magnetic field, and a net magnetization is created. Let me show you this video. Okay, so you see, for instance, in the absence, in that currently the spins are precessing with a certain frequency, okay? And this frequency is corresponding to the frequency of the system. And whenever we send an RF pulse to these precessing spins, which means we are adding energy, and then with this energy addition later on, once we remove the RF pulse, we will end up generating the signal. So let me also show you here. So as you see here, we have the spins again precessing, and when an RF pulse, like you see on the top, like the sync pulse is applied, you see the spins change their orientations, okay? So they are no longer in their initial form, but once the RF pulse is turned off, they are going to come back to their original form, and during that form, during that returning back, they are going to generate the signal. And here you see the signal, and once the signal is Fourier transformed, you end up obtaining a spectrum, and this is the one we usually use in high resolution NMR. So every proton has a magnetic moment. The magnetic moments of protons are aligned either in the same direction or in the opposite direction with the external magnetic field. And the former one, the ones in the same direction, possess a lower free energy than the others. The number of protons that are aligned in the same direction with the external magnetic field are slightly higher than the one that face the opposite direction. This slight difference is enough to create a net magnetization, to create a net magnetic field in the sample in the Z direction. And this magnetic field is usually referred as longitudinal magnetization. So you have the spins precessing in the parallel direction and also in the opposite direction with the magnetic field. And we have a net magnetization, and this net magnetization is known as the longitudinal magnetization. Well, on the other hand, we also have a magnetization on the XY plane. And the magnetization on the XY plane is called transfer magnetization. However, when we talk about the transfer magnetization, we know that the precessing protons are not in phase, which means that in the XY plane, we are not going to find all spins at the same spot. So the protons precess at the same frequency, but they are not at the same position at the same time. An illustration is given, as you see in the slide. So the randomly precessing protons cancel each other, and the net magnetization along the XY plane normally becomes 0. To tip away the net magnetization from the Z-axis to the XY plane, usually we apply an RF pulse. And when an RF pulse is applied, precessional movement of the protons get in phase with each other, giving rise to a net transfer magnetization. Okay, now let us try to visualize this in our mind. So we have the spins which were precessing and parallel to the magnetic field or opposite to the magnetic field. But in overall, we have a generated in the Z direction a net magnetization. And then we applied an RF pulse. RF pulse is in this in the range of RF range, which I have shown you in the electromagnetic spectrum. So what is going to happen is these net magnetization is going to be flipped with this energy to an XY plane. So the top, consider this as the Z direction, and the horizontal as the XY plane. So we have the net magnetization being flipped, and in that case, we have created the transverse magnetization. So before the RF pulse, we have randomly spinning net transfer magnetization, and then with the RF pulse, we let everything to be in phase, and we have the transfer magnetization. So some of the protons align themselves opposite to B0, in that case, which causes a decline in longitudinal magnetization. And what is going to happen is, when RF pulse is removed, the protons turn back to their previous state. And this process is called relaxation. So let's try to visualize this in mind. We have the net magnetization. We applied an RF pulse, and we flip the magnetization to the XY plane. But this RF pulse will not stay for all the time there. So you're going to remove the RF pulse for some time. Let's say 2 microseconds. You apply the RF pulse and you flip the magnetization. Once you remove that, this magnetization will come back to its original form, which the process is known as relaxation. So, and usually in order to flip the magnetization to the XY plane, we talk about a 90-degree pulse. In other words, a 90-degree pulse means a pulse duration which is sufficient to flip the magnetization by 90 degrees to the XY plane. That is what is meant by the 90-degree RF pulse, and this 90 degree is usually known as the flip angle. And in imaging, for instance, time to time, we use different flip angles, like 60-degree flip angle, and we can flip that magnetization only by 60 degrees, but it will still create a transfer magnetization. Okay, so the relaxation of longitudinal and transverse magnetization is measured to obtain information on the sample. And here you see the states of disturbance and relaxation through the chains of the net magnetization. And in fact, this process is mostly what we are measuring in time domain NMR, the relaxation times. T1 and T2 will be given to names. I will explain them explicitly, but this is what is usually we are measuring most of the time in time domain NMR. So the return of a spin system that has been perturbed away from equilibrium back to the equilibrium is what we call as relaxation. So we added energy to the spins, and then the energy was, this was only for a shortened term. So what is going to happen is it is going to be transferred back. So we have a transfer of energy, the result of the fluctuating magnetic fields. And based on the relaxation phenomena, we talk about two different relaxation. One of them is the longitudinal relaxation. The other one is the spin-spin relaxation. So spin lattice relaxation is known as a longitudinal relaxation. Spin-spin relaxation, also known as the transverse relaxation. And one is denoted as T1, the other is denoted as T2. And when you look at the signal expressions for these two relaxations, you see that in the case of spin lattice relaxation, we talk about a recovery. On the other hand, in spin-spin relaxation, we talk about a decay. Let us understand it much better. Okay, so initially we have a longitudinal magnetization. We flipped it, and how did we flip it? We applied, let's say, for RF for a short duration. So we no longer have any longitudinal magnetization. So what is going to happen is, as the spins are relaxing back, we will have a longitudinal magnetization that is recovering back. On the other hand, on the XY plane, this transfer magnetization will slowly disappear. So that is why for T2, we have an exponential decay. However, for T1, we have a recovery. And you see that in these equations, the signal mz is a function of m0, which is directly related with the number of protons, okay? And it is proportional to the T1 of your sample. So T1 and T2 are the relaxation times characterizing the relaxation behavior in your system. And these two relaxation terms are the ones we will be using in food systems to obtain information how our food samples are behaving, for instance, in a different storage environment or when the formulation is changing. Well, to carry out an NMR experiment, usually we do not use a single pulse. We might use just a 90-degree pulse to flip the magnetization, but we can use also some other pulses to make some other meaningful measurements. So over there, you see a pulse diagram. For instance, in this pulse diagram, we have a 90-degree pulse, and then after some time, you see that there's a 180-degree pulse. So what is a 180-degree pulse? How can we visualize this? So think about the magnetization as flipping up, okay, net magnetization. We said that if you apply RF for a certain duration, which will be sufficient to flip it 90 degree, so this is a 90-degree pulse. On the other hand, if you keep RF pulse longer, you can flip it 180 degree, which means the 90-degree pulse duration will be half of the 180-degree pulse. And then you can apply 90-degree pulse one more time, and the time difference between these two 90 degrees is usually known as the repetition time, TR, which is a parameter that we are going to set when we do a relaxation time measurement. Or we are going to see that if you apply a 90-degree pulse and then the RF pulse is removed, during that time, we have a signal generated. That signal is known as pre-induction decay. So in the signal axis in the slide, you see that after the 90-degree pulse, we have a signal generated. And if you apply a 180-degree pulse after a 90-degree pulse and wait some time, you see that we will have another signal, which is basically like an echo. And it is something that we will be using when we measure the spin-spin relaxation time, which is the T2 relaxation time. Okay, here you see again the pulse sequence. So we have a 90-degree pulse. This 90-degree pulse, after 90-degree pulse, we have a signal, and be careful that that signal is decaying exponentially. Okay, so we can have different types of pulse sequences, and we can apply another additional term to that pulse sequences, which in Dr. Morris' lecture you might see the gradients, because usually to do imaging we will be needing these gradients. Okay, so longitudinal relaxation time, T1, also referred as spin lattice relaxation time, refers to the time it takes for spins to realign themselves along the axis of the external magnetic field, and is computed from the recovery curve, which you see here. And the decay constant, the recovery constant of that term is known as T1 relaxation time. So here, let me show you how we are flipping the magnetization with the RF pulse, and then how the magnetization is recovering back. Okay, let us watch this again. So we have the magnetization, which is processing, net magnetization. We applied an RF pulse, we flipped it, and then it starts to recover. Oops. Now let's look at this in terms of the T2. So here, how the transfer magnetization is disappearing and also be seen. And here you see how T1 curves look like. So basically T1 is a recovery curve, and with this recovery curve you just do some fitting and you obtain the T1 relaxation time. Well, local fluctuating fields basically contribute, if you look at the physical mechanism of the T1 relaxation, normally we see that this net magnetization recovery is related with the collective ensemble known as the lattice. So spin lattice relaxation is related with the whole lattice. So, and the coupling between the lattice and the system is specific. So we have an energy transfer between the spin and between the whole system, which is called the lattice. On the other hand, transverse relaxation time refers to the time it takes for transfer magnetization to decay to equilibrium. So you see we have an exponential decay. And depending on whether you have oil or water, this decay will be different. Or if you have a sample where it is really very heterogeneous in terms of components, again, you might have really a very short decay, a very fast decay, sorry. And the transverse magnetization is usually denoted by this exponentially decaying curve. Well, T2 is a measurement of how long the spins have phase coherence with each other. Sometimes spins dephase and lose signal, but still have a well-defined phase relationship. So in that case, it's possible to rephase the spins so that they are in phase and thus generate the signal. So rephasing of the spins usually generates an echo, and that is what we usually use in the measurement of T2. So 90, 180 is actually a refocusing pulse, which helps to bring the dephased spins in phase, and then we generate basically an echo. So after 90 pulse, we can apply another 90 pulse, and the time difference is TR. And the time difference between the 90-degree pulse and the time between you obtain the echo is also known as the echo time. And these are all going to be the parameters that we are going to learn, we are going to set while conducting an NMR experiment. And in fact, this generation of echo, this pulse sequence is basically defined as spin echo. So we have 90-degree pulse, 180-degree pulse, and later on we have an echo generated. Let me show you an animation here. So 180-degree pulse is applied, and then you obtain the echo. And then it is decaying. So 90-degree pulse, 180-degree pulse, echo is generated, and then the signal is disappearing. So these points to the way to measure T2. So we repeat the experiment with different echo times, and then by looking at the maximum amplitude of each echo, we can easily obtain a T2 decay. And physical mechanism of T2, well, T2 is known as spin-spin relaxation. Why we have dephasing? Because the spins exchange energy with each other. One flips up and the other flips down. This leads to a change in frequency. So both are in slightly different fields, and it results in a dephasing in the XY plane. And there's a very famous sequence that is used to measure T2, which is CPMG, and Purcell-Maybom-Gill sequence. It's all denoting the initial names of these scientists. This is an ideal version of the spin echo, and T2 is a measure of the phase coherence in the XY plane. So let me show you that. So we have the 90-degree pulse, 180-degree pulse, and what we do in CPMG is we are repeating these 180-degree pulse, and then we are collecting the maximum echo amplitudes. So we record the T2 relaxation. And again, the relaxation, that is what I mean. The 90, 180, we have echo, and then we have other echoes with increasing echo times, and we end up obtaining a T2 curve. Well, let me show you in that case one important point. If you just look at the decay in FID, in pre-induction decay, what you are measuring is usually T2 star. On the other hand, if you look at the decay in the echoes, what you see is the T2 decay, the T2 relaxation. So with increasing echo time, we end up obtaining increasing decaying signal, and that is helping us to generate the T2 decay curve. Okay, so let me show you again here the relaxation. So this is flipped. This is how the echo is generated. So let us look at again. We have the dephase spins, okay? They were flipped 180 degree. So we have phase coherence to increase the signal so that we have the echo generated. Okay, here's some examples T2 signals. And let me also show you here the T1 and T2 together. Let us look at again. T1 is recovery, T2 is decaying. The thing is, in food systems especially, you do not have just one T2. You have multiple compartments, and multiple compartments lead to usually more than one T2. For instance, here we have a CPMG decay. If you apply a mathematical transformation, you obtain a relaxation spectrum where you have different peaks. Do not confuse it with the NMR spectrum that we discussed in the very beginning. These peaks do not tell us that they are individual chemical components. Like it doesn't tell you that this is organic acid A, this is organic acid B. This shows us that the relaxation behavior in your sample is multi-exponential. So you have different relaxation behavior. A very basic example. For instance, if you have an emulsion system, oil and water. Oil and water has different relaxation times. If you measure if you apply a T2 experiment and then apply this transformation, you will obtain two peaks coming from oil and water. But why is this the case? Because oil and water has different relaxation times. On the other hand, if you have, let's say, acetic acid or one type of vinegar, in the vinegar, you may obtain just one peak, one relaxation time, because T2 might not be sufficient to tell you what other components exist in the vinegar. However, if you have distinct relaxation times, this is kind of the behavior that we would see. Another example, plant cells, like a fruit or vegetable. If you put a fruit and vegetable to an NMR tube and you conduct a relaxation measurement, you will obtain multiple peaks like you see here. And research have shown that these peaks could come from the organelles that are present in a plant tissue. For instance, in a plant tissue, vacuole is the organelle which usually has the highest water content, so the longest relaxation time is usually associated with the vacuole. Cell wall cytoplasm also has distinct relaxation behaviors. So how come I can use this information? So if you have a fruit, if you obtain this T2 fingerprint, and then if you apply a process to your fruit, you will see that your relaxation spectrum will be affected. Maybe you will disrupt the tissue so that all compartments will merge, or you will keep the integrity of the tissue. So I will show you with examples how this relaxation spectrum can be used. Okay, so here you see the T1 and T2 differences. So T1 relaxation time, also known as the spin relaxation time, indicates the effectiveness of the magnetic energy transfer between the protons and the surrounding lattice. Pure bulk water has a very long T1 time. Oil, on the other hand, displays a shorter T1 time. The change of the state of the oil and water, as well as their interaction with their surrounding molecules, can significantly affect the T1. T2, known as spin-spin relaxation, is a measure of the effectiveness of energy transfer between neighboring spins and is shorter for closer proximity between molecules. So T2 is usually the shortest in solids, and resulting in a higher energy transfer between efficiency between the spins, followed by oil and water. So water also has a long relaxation time, T2 relaxation time. T2 relaxation measurements coupled with the relaxation spectra. So this that I showed you here is a relaxation spectrum or relaxation spectra for multiple ones. So T2 relaxation spectra are known to yield information on water content, physical properties of the water with the surrounding molecules. Well, T1 and T2 of water, oil, crystals, and solids could also show differences, especially in the case of T1. Crystals show quite long T1 times. Like here, there is a table, and you see, for instance, T1 of glucose is 16 seconds. So for glucose, recovery is very long. On the other hand, if you look at for sucrose, crystalline sucrose, T1 is around 1.3 seconds. And for icing sugar, it is again around 1.3 seconds. For lactose, we talk about the higher T1 because lactose also has quite good ability to crystallize. And the more crystals we have, usually we know that T1 times will be longer. On the other hand, T2 times will usually, almost in solids, will be shorter. Because whenever we have sugars, we are binding the water protons and we are letting the exchange, the transfer to be done very efficiently, so the T2 becomes very fast. Which we did not talk about details yet, has many food applications. So what are these applications? So it can be used in post-harvest to understand post-harvest behavior of different processing methods on fruits and vegetables. On meat tissue for the analysis of the post-mortem muscle, for dairy applications, for analysis of cereals like dough and baking processes, it can be used. So let me show you some examples for post-harvest physiology to monitor the physiological change during development, like ripening, storage, and processing stages. We can use NMR relaxation times because during ripening, the compartmentalization in the cells change. Thus, they can easily be reflected on the relaxation times. And the relaxation times, as given in the relaxation spectrum, can tell us whether the cell is disintegrating, disrupting or not during these physiological changes. we can detect the complications in tissues. For instance, chilling and freeze injury are problems that could affect specifically the citrus fruit significantly. And T2 relaxation times are known to decrease due to freeze injury, since cells are disrupted, back wall is leaked out, and we have a decrease in the relaxation times. In pomegranates, there is a disease called Blackhearts Disease, and in studies it was shown that these pomegranates showing Blackheart Disease had a different relaxation pattern. Or we can detect variation in permanent quality attributes owing to the plant's variety, location, or cultivating season, again by looking at the relaxation times. Well, in post-mortem muscle in analysis of the meat, well, we can look at the quality, we can have a quality evaluation, like evaluate the meat freshness. And meat, the muscle tissue, is a perfect material for low field NMR studies for measuring T1, T2, because water is usually the main determinant that will affect this freshness, and the water status can easily be obtained from relaxation time measurements. Or other processing conditions, storage conditions, cooking, restowing, they all can have an effect on the meat tissue, on the flesh tissue. You can all quantify these by using the relaxation times. NMR is ideal for characterization of dairy products due to their high water and fat content. That is why it can be used to estimate the liquid fat population in the milk, or monitoring post-production changes in ice cream crystal structure, measuring the degree of gelation, examining the changes in milk during cheese production, brining, or ripening of cheese. We can all obtain different information. Well, in cereals, the most frequent use of NMR or MRI involves moisture migration into cereals, moisture loss accompanied by crust formation during baking, or transfer of water during boiling of pasta. Analysis of water content, mobility and distribution, as well as measurement of fat content, analysis of structural changes in various foods as macromolecules, examination of physical, chemical, microbiology quality, online monitoring and process control, inspection of rheology, like in dough materials, for instance, relaxation times can be used. Well, let me give you some specific examples. For instance, there is an already determined standard method to measure the solid fat content of fat-containing products, like even the margarine, butter, chocolate, cocoa butter. We can measure the solid fat content, because in these mixtures, in these products, we not only have liquid fat, which is oil, but also solid fat, which affects the physical properties significantly. Yesterday, we talked about chocolate crystallization. Crystallization in chocolate is affected significantly by the solid fat content. And measuring solid fat content is quite easy in terms of NMR. We don't need a complicated pulse sequence. We can just use a 90-degree pulse, record the FID, and then with a data analysis, by looking at the data the signal intensity at different points, we can come up with the solid fat content. And usually, in order to do this, of course, we need a calibration curve that is done in an instrument like this one. And most of the time, the instruments guide you on how to set up the calibration curve. So solid fat content is one example. We can measure oil and moisture content in dry products like in seeds. And in order to measure oil and moisture content, for instance, in sunflower seeds or in any other seeds that you can think of, we can measure oil and moisture content. For that purpose, we usually use the sequence which we have discussed, the spin echo sequence. So we have a 90-degree pulse, 180-degree pulse, and the signal amplitude that is recorded at the 90-degree pulse gives us water and oil signal, and then the echo signal, which is acquired after 180-degree pulse, gives us the oil signal only. So thus we can easily obtain, we can easily quantify the oil content of the seed. But the important thing here is we usually cannot use this approach for measuring the moisture content of all foods. So usually foods should be below a certain moisture content, because if the moisture content is high, the echo signal that you see in the slide, which is normally supposed to contain oil content only, will include water signal as well. That is why to measure water content of other foods, some modifications have to be done on the sequence. Well, parallel with this, let me talk about some non-food applications. For instance, hydrogen content of fuels can also be calculated with a similar approach. The rock core analysis, here you see a 2 megahertz, a very low field system, where you can determine the oil distribution in rocks, which is kind of a application that is frequently used by the petroleum industry. By the textile industry, oil pickup by fibers is used again with a similar sequence. This is known as spin finish. So for the textile industry, it also has a use. Well, a compact NMR relaxometry device has been used to investigate blood and blood components, so that the researchers, for instance, try to find correlations between some other parameters, like with some disease indicators, just by looking at the relaxation times. NMR can also be used as a powerful tool in cultural heritage. Well, portable NMR devices are present in the industry. For instance, here we have a single-sided NMR measuring moisture in a wall painting date back to 15th century that is in Italy, and you can measure the moisture content of the wall to see, for instance, if there's any water migration coming from some part of the structure which is going to disrupt the paint, let's say. Well, let me now give some examples from our lab. Well, we have used, and I will go these examples very quickly because we don't have enough time. For controlled release applications, we on gel systems, we can use NMR relaxometry. And yesterday I said that confectionery systems are also gels. So we can easily utilize gels, the NMR techniques in confectionery gels as well. For instance, here we try to understand the release behavior of an antioxidant from gels made by using different hydrocolloids. Since these hydrocolloids has different interaction with water in the gel structure, they resulted in a different relaxation behavior. And similarly, and in parallel with that, spin-spin relaxation times changed. I'm going to emphasize more on some other applications. For instance, this is also one of the applications that we really use NMR effectively. We worked on a system called liposomes. Liposomes are some encapsulation systems where we can easily encapsulate active agents into the liposomes, and liposomes are capable of trapping some bioactive agents inside, and once they are disrupted, that is an indication of their instability. For instance, here you see a liposome which is being destroyed, and the mechanism of the lipid chains in the liposomes have been detected by NMR relaxometry measurements, which means T2 measurements, because depending on the free water content in these liposomes and these capsules, T2 relaxation times have changed. Okay, now switching to another application, which is also a very nice food application that we have shown. Well, in our lab, we are working on different hydrocolloids. And remember that yesterday in the gels section of my lecture, I said that hydrocolloids can be used to create soft candies. Well, in this study, we looked at a different hydrocolloid, which is a kinseed extract that is obtained from the seeds of the kins. Well, what we have shown is kinseed extract has potential to act as an emulsifier. So, a hydrocolloid which has a potential to act as a emulsifier. Well, emulsifiers are important in the stabilization of emulsions, and food industry continuously seek ways to find natural emulsifiers that are capable of stabilizing the emulsion, because there are also synthetic emulsifiers. And by using NMR relaxometry, it was possible to show whether a hydrocolloid can act as an emulsifier or not, because when an hydrocolloid is absorbed onto the oil droplet surface, it is relaxation behavior, it is changing. Thus, we can get indirectly information that this hydrocolloid has the potential to act as an emulsifier. Well, I'm not going to talk about the details of that study, but we had many other results which supported this finding. Well, double emulsions are another category of foods where we are using double emulsions to create low fat content food products. And whenever you have oil and water in a system, NMR relaxometry is a perfect tool to characterize that system. So the stability of double emulsions or multiple emulsions can easily be assessed by NMR relaxometry. Well, this study is a study that we had performed on plant cells. For instance, in the study, onion has been exposed to pulse electric fields to increase its extraction efficiency, to increase the efficiency in the extraction of the bioactives from onion. And what has been shown from the relaxation time distribution is that with different pulse electric fields combination treatments, the integrity of the onions have changed. For instance, here you see 5 peaks. These peaks have been identified as different cellular structures in the onion. Okay, we also worked on another study where we investigated freeze-thaw stability of mangoes. This was a study that we did with our Thai partners when I was in the US. And what happened is mango is a fruit which is really preferred to be used throughout the year. That is in other countries. This is not the problem in Thailand, but the Thai scientists were asking us the question, okay, we are trying to freeze these mangoes by using different approaches, and we wonder whether the cell integrity is kept when we thaw them, because as ice crystals get large during freezing, the cellular structure is disrupted, fruit tissue is lost. But with some techniques like calcium addition or enzyme addition, we can prevent this. And we were able to show that these treatments like calcium or enzyme treatments did not affect the cell integrity significantly. So I'm skipping the tomato example. Okay, for instance, this is another study which was done in our lab, an MR study of hydration of the bean during cooking. So hydration behavior of the beans has been assessed by using relaxometry. Okay, this is what the Blackhearts disease that I mean in pomegranate. So Blackhearts disease results in the pomegranate arils to be black. So this is basically a spoiled pomegranate. And whenever you look at the relaxation times of this pomegranate in overall, we observe that the 2 times were significantly different, and we had a different relaxation spectrum profile. Again, freeze damage in mandarin orange has been studied by using relaxation times. So relaxation times was a good indicator that showed the how freeze damage, freeze injury changed the tissue, the cellular structure. Okay, I would like to show a new technique that we are going to use in SuChAQuality for confectionery products. Well, for the last 2 years, with the help of Dr. Grunin, we have been working on using some sequences like magic sandwich echo sequence to understand the crystallinity in certain food systems. Well, this magic sandwich echo sequence help us to identify the mobile and rigid phases, but most importantly, with the approach hypothesized by Dr. Grunin, we were able to differentiate in this rigid region the amorphous and crystalline fraction. Well, why is this important? Let us discuss this. Well, especially in terms of candies, we consider a hard candy. A hard candy is a glassy substance because it is obtained by rapid cooling of the hot sugar melt. So it is an amorphous, which is equivalent to a glassy state. And amorphous materials has the ability to absorb moisture quickly, and that can result in stickiness. On the other hand, in a hard candy, if the hard candy is breaking up very quickly, that means that it is amorphicity is not maybe it is very brittle, so the degree of amorphicity is quite high. That is why it is breaking up quickly. In that regard, if we have a tool which we can measure the degree of amorphicity in a hard candy, that could be a way to make conclusions about the behavior of that candy in the processing line. And for that purpose, when we first come up with this hypothesis, we worked with some sugars, powdered sugars. And what were these powdered sugars? Well, we created simple crystalline and amorphous models. Like we freeze dry the sugars to obtain amorphous forms, and we also used control crystalline forms, and we measured by using this magic sandwich echo sequence. Well, the results were promising, and we are still working on that. We were able to show, for instance, that amorphicity can easily be predicted. And then this information was further used on explaining another phenomena in hard candies, for instance, graining. In other words, crystallization. Crystallization in a hard candy is not something we want. So measuring the degree of crystallization is also an important quality parameter. We did this amorphicity, crystallinity measurement on starch samples, on different starch samples. This study is still going on. We also looked at honey in terms of understanding the crystallinity, because in honey we normally don't want to see crystals, and if it has crystals, usually we want to melt it, and in industry different processes are used for melting the crystals in honey. To quantify the crystal amount in honey, again similar approach was used, and one of my PhD students is currently working on using this approach to understand stickiness in powder foods. For instance, whey powder, for those of you who maybe use it as a protein shake would know better, whey powder also has the ability to form cakes, to agglomerate. To prevent this agglomeration, anti-caking agents are used, but understanding the caking tendency of whey powder is important, so that we will understand, we will be able to predict its shelf life during storage. So this is something that we are still currently working on, and this crystallinity amorphicity approach is something that we will be focusing on SuChAQuality in a detailed way. So for the secondments that are going to be done in resonance systems, most of the time you will try to use these sequences, solid echo, magic sandwich echo, or spin diffusion sequences, to understand this amorphous crystalline behavior. Okay, I went very fast on this application session, but this was just to show how time domain NMR can be used for different food applications, and we can generate many more food applications. And in SuChAQuality, we will also be developing new ways, maybe solving new problems on the confectionery sector, and maybe also on other food materials.